finite element implementation for non-local convection diffusion and mechanics. And this is joint work with Volker Schulz and Christian Vollmann, also from Trier University. So so I'll basically present you one function which is around the following problem. So we are given some compact base domain that's a 2D domain, and we now consider a domain omega which is open within that domain. So that is where our solution lives, or the degrees of freedom live. And we are then given also a complement of that gamma, where we could put some Dirichlet boundary data. So we call that interaction domain, but that set could also be empty. And the operator we look at is this non-local operator here, classical case where we have a truncated interaction horizon B dot delta, where this truncation could be, for example, an L2 ball or an L infinity ball. And then we have some kernel CXY, which can be matrix valued or scalar, and it behaves like fractional type for a small xy, or even like an integrable kernel or constant kernel or something like that. So this is the setting which we look at, and this is what this code or this function which I present you will be able to assemble, so set up. The problems you can solve with that simple, for example, Dirichlet type problems, where we have the unknowns on omega and some Dirichlet data given on the non-local boundary gamma. Whereas if you have that gamma is empty, then we get to some non-local Neumann type problem. So what we have is a flexible finite element implementation for that problem with a Python interface, which is for researchers and which runs at convenient speed, so to speak. So again, what it does is linear finite elements of what the code does and what it doesn't do. So basically, we have some possibilities to have continuous Galerkin and discontinuous Galerkin linear finite elements on rather complex 2D domains with different types of kernels up to truncated fractional type kernels. And we also have some multi-threading capability in that code. But what's not part of it, so what it doesn't do is, for example, mesh-free kind of thing or sophisticated state-based peridynamics. That's completely out of scope, so that's not part of that. It has very limited capabilities in 1D and 3D. And also for large horizons, actually, it's not very efficient. So there are other techniques for very non-local settings. And what we look at here is basically a function which generates from some elements and labels and vertices and some kernel and furniture rules, which we put into the configuration, a stiffness matrix A. Okay. So examples for the kernels could be, could be, for example, this fractional type kernel, which you see in the first line. And then if you put different a jump on the right-hand side, for example, you can see in the picture on the right side how it smoothens out, for example, this jump. A simple example for a matrix valued kernel could be this peridynamics type kernel, which you see in the second row. And there you see on the right side, on the bottom, you see a deformed kind of circle or something like that, which you can get from that kernel. So those are the things which are possible, but we also have some possibilities for labeled kernels. So you can have a kernel which depends on labels of the domain. So you see on the last picture, on the fourth picture, some domain which is 0 due to the fact that there's a forcing term, but no interaction due to this label dependency. So those kernels are part of the C++ implementation, but you can choose them with those Python dictionaries, which you see here, for example, the constant kernel would be then function constant or something. And that is the way you choose those. Okay, there's a set of kernels. For the domains, we have different labels, which then identify Dirichlet boundary or the degrees of freedom. And we ignore labels which are 0, which helps a bit to cope with more complex domains. Like if you look at the right side, you see there a case where there's a hole, and that leads to a non-disjoint interaction set. If we intersect the interaction set with the domain, it becomes disjoint, and then you get somehow errors in this representation of the operator. But then with artificial elements, you see there on the right side, you can efficiently cope with that, even though we use a breadth-first traversal of that interaction set, which is more efficient than, of course, touching all pairs of elements and checking whether they interact or not. So that way we have some possibility to efficiently deal with complex domains. Of course, also, if you use that technique, you can solve problems on disjoint domains, as you see here in the fourth picture. So that white space, there's actually nothing. And we connect those lines, the local boundaries, so to speak, with one artificial vertex, which is ignored in the integration, but it's used for the traversal, and then it allows to check efficiently for interactions between disjoint parts of the sets, or very, like holes or something, other complex settings. Oh. Another thing is that we have different truncation routines also implemented, like L2 ball or L infinity ball. You might get some asymmetries there due to this approximation, but we can somehow guarantee that the finite element approximation is always symmetric if the bilinear form was symmetric. And that also helps in the case of gamma being empty, because then a singularity in that matrix, it's not irregular. And this null space is exactly the constant vector that can be of some importance. So those kind of settings, which approximate ball you use for the truncation, which quadrature rules in the ansatz space are part of another dictionary, which you set. And then basically, you put all of this, what you saw, like the kernel and the elements with all their labels, into that function, and that spits out the stiffness matrix. Yeah. So one last point about the speed. So again, there is some multithreading capability. So we use OpenMP to parallelize a bit the computation, and made as scheduler. This is necessary because otherwise you get unnecessary effort in terms of memory consumption for the different threads. And we can scale up, for example, from a problem with 24,000 degrees of freedom from 35 minutes to 80 seconds on a sufficiently large computer. So it's not a cluster or something, it's just one computer, and you can scale so that you can also run larger instances for experiments or something. Yeah, so that was basically it. I hope I'm still in time. The code can be found on our GitLab repository of the university. There's also some kind of documentation for those functions which you want to use of this Python interface. And if you want to join the tutorial next week, then you need to run a running Docker instance. And then you can pull simply pull the image on that repository and run a Jupyter notebook where everything is set up correctly. You can also, of course, install everything yourself and try it out. Yeah, okay, I think that's it from my side.